Hi, my name is Rostislav Zinko, and I would like to introduce the Building Databases with Redis video course to you. During this course, we will walk through the very basics of the interaction using the Redis database to complex data structures, database design decisions, and use cases. So, let me start with a small introduction to Redis. Redis is a database based on key-value storage. It means that it does not have tables and a predefined scheme like the classical relational databases have, for example MySQL or PostgreSQL. At the same time, it does not allow us to store complex multi-level documents like the popular NoSQL database MongoDB does. Redis operates using keys and values, and this data type is usually called the hash table or dictionary in other programming languages. So basically, the whole Redis database is just a mapping of string keys, which are unique throughout the database, to the corresponding values that can be of string, list, set, or hash data types, all of which we will discuss throughout this course. At a glance, it seems that only the simplest things can be done with such a simple storage design, but there are techniques and tricks that allow you to use Redis as the main storage for your applications. Another positive side of such a structure is the blazing fast speed in the execution of queries. This is the reason why information technology industry giants such as Twitter, Stack Overflow, GitHub, Flickr, Microsoft Azure, and others use Redis for their needs. So let's start by getting the Redis project from its home, located at redis.io. First of all, we have to visit the Downloads tab on the website and choose 3.0 version of Redis to download. Redis supports only OS X and Linux platforms officially, but you can scroll down and follow the instructions if you would like to install Redis for Windows. We will use Redis version 3.0 during the course. Though this version is not yet stable, it incorporates all the features of the current stable Redis version and also offers new features that will be available soon in a stable state. After downloading the archive, we have to build the project manually from source. Unfortunately, the Redis project does not have ready-to-use binaries. In order to perform this, we will open our terminal, move to the folder where we have the unarchived Redis source, and run the make command, which becomes available as soon as we install the Xcode and Xcode developer tools from the Apple App Store. Now, it will take some time to compile and link all the components of the Redis distribution, and we're interested in two of them, Redis Server and Redis Client. When the building process is complete, we are ready to use the newly installed software. The binaries we need for now, namely Redis Server and Redis CLI, are located inside the src subfolder of the current folder in which we built Redis. So the next thing we have to do now is start the Redis database server by running src/Redis server. After entering this in command line, you will see a small greeting and server log in your terminal window. Redis uses a simple configuration file to get the initial server settings, but it is also available to configure the server in runtime directly via Redis commands, which we will cover in section 2. So, once we have the server up and running, we can move to the next checkpoint, connecting to the server and executing commands. In order to get access to the server, which works through its own network protocol, we have to run the client, which is the src/Redis CLI application. Let's open another terminal tab and type this in it to start our client that automatically establishes connection to the server. If everything is working correctly, we will see a prompt that consists of the server IP address and port. This means that a connection is established and we are ready to run commands. Note that we're using the client on the same machine on which the Redis server is installed. However, if you have a Redis instance running on a remote machine, you have to specify the host to connect to using the -h command line option. Let's type exit to finish the client session and use this option to connect to the server. In my case, it is localhost. As you can see, it worked, except that the prompt text was changed. In this video, we downloaded and installed the Redis server, and you learned how to use the client to make a connection to the server. We also performed our first command called exit to stop the Redis client gracefully. In the next video, we will take the first steps in data manipulation in general, and you will learn how to get and set values for keys in particular. We will also start discussing a simple wiki application built with the Python language and the Redis database at the main storage. In the previous video, we set up the Redis server and you learned how to connect to the server using the Redis command line client. Now we are ready to get to the real work, namely manipulating data. As was said in the previous video, the Redis database is a big distributed hash table with unique keys mapped to corresponding values that provide extremely fast query execution. The first thing you have to learn is how to insert, read, and delete data from the database. Technically, inserting data into Redis is an operation of setting value for a certain key. The easiest way to insert data is using the set command. It takes two mandatory arguments, key and value for that key. Let's open the Redis client in the terminal and try to perform the set hello world command. The client returns OK if the value was successfully set for the key. It can be handy to set more than one value for more than one key with one single command, and that is why the mset command exists. It allows us to pass pairs of keys and values to be inserted into the database in a single query, which is faster than sending several single set queries and prevents other queries from slipping between those set calls. Let's type mset hello1 world2. This corresponds to two separate set commands, set hello1 and set world2. Well, OK means that the operation is successful, but it would be much better if we could get values for those keys manually to ensure that everything is really OK. That is what the get command is for. It takes one argument, the key, and returns value for that key. Let's check it by typing get hello. Yeah, we see 1 on screen, and it is exactly the value we set earlier. However, remember that we've been typing set hello world right before the mset command. It appears that the mset command has rewritten the value for hello, and this is how set and mset work. They will set the value for the key or overwrite it if such a value already exists, without any warning. So be careful with that. The same goes for mget as well. The mget command helps to get several values for several keys in one query. Let's type mget hello world. Here we can see a list of values the database has returned to us. The last command we have to discuss is the getSet command. It sets a new value for the key while returning the previous one if one was set earlier at the same time. The most common use case of the getSet command is the resettable counter. We will talk about the counter in the next video, but you are always free to get your creativity to work and find other usages of this command. This can be very convenient if you want to set a new value for the key while you would like to receive an old value for some calculations in your application business logic. So, for now, we are aware of the basic operations on keys and values, but we have not talked about the data types we are working with. Well, the Redis storage is typed, and we know that at the highest level, the Redis database is a hash table that contains keys and values. All those keys and values we were working with earlier were of the string type. String is the main type known by Redis. Actually, Redis does not operate numeric values at all, and the most basic type is string with a maximum length of 512 megabytes. Another interesting thing is that string is the only data type available for keys, while values can be of data types such as lists, sets, hashes, and sorted sets, which we will cover in detail in the upcoming sections of the course. At this point, we are aware of the basic operations done on strings using the Redis client, so let's watch what kind of database can be designed using only this knowledge. From now on, we will work closely with code samples that are available for download along with this course. Let's open the Section 1 folder where the simplest wiki application implemented in the Python language is located. I don't expect you to be familiar with Python, but it's a pretty simple language that provides a very simple API to access the Redis database, which almost exactly duplicated Redis commands names and parameters. Using Python also does not mean that this is the only programming language to work with Redis. Redis has clients for countless number of programming languages. Also, the simplicity of the Redis protocol makes writing your own drivers easy. Let's open wiki.py. You can use your favorite text editor for this purpose and run the application in terminal by typing python./wiki.py in it. You can find detailed instructions on how to prepare your environment to run the application on different operating systems in the readme.txt file shipped with these sources. Here's a simple wiki application that implements a plain collection of pages without any hierarchy. Let's add some pages by clicking on the Create New Wiki Page link and fill in some simple text data in the title and text fields. When done, let's move to the Redis command line client in the terminal and type keys space asterisk. The next video will discuss this magic to see all the keys in our database. Let's analyze pages title first wiki page key. Its structure seems quite strange, but this is a trick to make our application execute queries of page text by its title. So basically, the title is the parameter prefixed by the page's string, which means that the title parameter is a wiki page title. Using title, we can get the text of a certain wiki page. Such a simple structure allows us to create, modify, and delete pages using get, set, and del commands. Wait, we were not talking about the del command, but it still exists and deletes the specified key and the value bound to that key from the database. You can also pass several keys in a row in order to delete several records from the database in one query. Let's try it in a terminal by typing del hello world and then get hello to ensure that the hello key does not exist anymore. Pretty simple for a whole wiki application. You can explore class page from wiki.py, where the view, del, and save actions interact with Redis to deliver application functions to you, having almost zero application logic inside. Pretty good for now. Now we can operate strings by setting, getting, and deleting data from Redis. Though it is enough to operate the wiki page's lifecycle, you can see that the application behaves like it is showing a list of pages. We have even used the keys command, and this is what we are going to talk about in the next video. In the previous video, we discussed how to insert, modify, and remove data from database operating strings. Actually, get, set, del, and their multiple key modifications work for all the data types, not only for strings. You will see this in the near future. This video is devoted to commands that work directly with keys that, along with the previous learning commands, do not depend on the value type bound to a certain key. First of all, we will talk about the type, object, dump, and restore commands. These commands primarily serve as debugging facilities and provide service information on values bound to certain keys. Let's start with a type command. We will begin our experiment by typing setHello1 and then type hello. What we see on screen is string. That's it. The value stored inside the hello key is of the string type. The next command is dump. It's a debugging command that allows us to receive the exact serialized representation of the value inside the Redis storage. Type dump hello, and what you will see is a strange encoded string of characters. The opposite can be done with the restore command. Well, dump and restore are completely useless for application developers, but they will help you if you would like to hack on the Redis source. You can visit Redis.io and go to the Commands tab to get more information on these commands. The last command that allows us to inspect Redis keys and values is an object command that accepts two parameters, subcommand and key. There are three subcommands, refcount, encoding, and idle time. They return the number of references to value, encoding of the value, and time elapsed since the creation of a value. Let's try these three subcommands on two different values, integer 1 and an arbitrary string. As you can see, the significant difference is in encoding. It turns out that though Redis does not expose numeric types, it uses the int type for strings inner storage in order to save some space on your hard disk. So this is what we have to know. Numeric values save space for us inside the Redis storage. Let's move on another block of commands, exists, keys, and scan. These allow us to receive a list of keys. The first command is called exists, and its purpose is to check whether there is a key existing in our database. It takes only one argument, the key. Let's type exists hello, and we will receive 1 as a result, signaling that the key exists. Otherwise, we would have received 0. The next important command is called keys. This command allows us to receive a whole list of keys restricted to a specified pattern. This pattern can contain question mark that represents a random character, asterisk that represents a random sequence of characters, and a set of characters in square brackets, which means a single character from that sequence. Let's try to type keys space asterisk. This will print all keys from our database. Then we can try keys page asterisk, and we'll receive a list of keys prefixed by the page string. You are free to experiment to get a better skill in writing patterns. The keys command is good enough when you are not going to receive a very big list of keys. However, when there are thousands of those, it is much wiser to use scan. Scan receives one mandatory argument, cursor, and two optional ones, match and count. They specify the pattern as in the keys command and the number of values to return in a single query. The returned value consists of two parts. The first one is a cursor name to continue to receive results in the consequent queries, and the second one is a partial list. If the first value is 0, the cursor is reset and all values are retrieved. Let's test it by typing scan 0 match page asterisk count 1. Here we receive a partial list and then scan, which in our case is 4. The last simple yet powerful command to learn in this video is rename. This command allows us to rename a key in one query instead of using 3 sequential get, del, and set commands. Let's type rename hello world and then get world to ensure that the key was actually renamed. That's all with theory for now. You can through the experiment with the newly learned commands, especially with can and keys. Let's get back to our Wiki application. As you've possibly seen, there's a list of pages at the root page of the Wiki application. This list is created using the keys command that you learned minutes before. That's it. Having no changes in the database, we have received a bit of new business logic for the application. Therefore, everything is as simple as that. Keys is not the best way to make such kind of task, because in general, the keys command is slow. However, this is our way out as we have not discussed lists yet. So far so good. Let's open our web application and visit any wiki page that we created. As you can see, there's a line telling us how many times the page was visited. We will discuss how this logic can be implemented using Redis features in the next video. In the previous video, you learned how to inspect keys. Among other things, it has turned out that string values can be stored as integers. Such a storage mechanism enables database to support features such as atomic counters. So this video is devoted to atomic counters and how they can be operated using Redis commands. Atomic counters serve as an effective way to add or subtract integer and floating point values directly on the server without writing application code. Let's start setting some value x to 1. We can use the increby and decreby commands to increase or decrease the integer value on some other integer value respectively. Let's try it in the terminal. We have to ensure that these commands work with integer values only. If there's a need to work with floating point values, we have to use increby float, which is the only command to work with floats. There is no decreby float command, but fortunately we can use negative values. Let's set another value y to 1.5 and try to decrease it by 0.25 by typing increby float y minus 0.25. Now you can try to experiment with increby and decreby to ensure that they will give you an error when trying to operate with the y key. Nice! There are also two other commands, incr and decr. They do pretty much the same, except that they increase or decrease the integer value by 1. These commands exist because such calculations can be done more effective than adding or subtracting arbitrary values. Let's type incrx and decrx to check how these commands work. Then, when we type getx, it shows us that the value is equal to 4 again. Now that we have all this knowledge, let's continue with atomicity. So, atomic counter means if you have a concurrent connection to the Redis database, the server ensures that the operation will be performed with the value atomically, not affecting the other connection. So, if we have value for x set to 1, and two concurrent connections perform the incr operation, it is guaranteed that one of them will receive 2 and another one will receive 3 as a result. The situation when both of them receive 2 is impossible. So, returning to our wiki application, it seems wise to implement the page visits counter using the incr operation. In order to not mess up our data, we will add another set of keys that start with page::views::page title and whose value stores the number of page views. You can find the corresponding source code in the page class where the view action is processed. At this point, we are done with atomic counters, and in the next video we will continue discussing operations on strings by learning partial string modification commands. In the previous video, we discussed how to perform arithmetic operations directly on the Redis database server and how atomic counters can be useful in real application. In this video, we will continue working with strings and we will discuss how to perform partial string modification and querying and how can it be useful in application. The first and the easiest way to modify string values is using the append command. The append command takes a string value by key and concatenates the second argument to a stored value in the database. Let's try it in a terminal. First, let's set the English key to hello string. Then let's append world to this string. Here we would like to add a space before world, so we will embrace the second argument into double quotes. Now let's check the results by typing get English. As you can see, we received hello world as expected. Let's try also the case when the value does not exist. For example, by typing append French bonjour. The result is not an error, and if we type get French, we would receive the same result that we would get when we use set French bonjour. This command is useful when you have to append some contents to the existing value at the same time, using less bandwidth and queries to perform the operation, which can be replaced with the get-set sequence otherwise. That's all on append. Another topic that we will cover in this video is ranges. So range is just a substring, and Redis allows us to make queries that return or modify substrings. In order to receive a substring, we will use the getRange command that receives a key, start index, and end index. Let's try and type getRange French 02 to receive the bone string. Except getRange, there's another command called setRange, whose purpose is to modify the range of characters in a string. This command's arguments are a bit different. While getRange accepts the start and end index of range, setRange accepts the offset and new value. Let's use this command to change bonjour to bonsoir. In order to achieve the result, we will type setRange French 3 soir. To ensure that everything was set as expected, let's type get French. At this point, let's return to our application. Open the website at the root page and inspect the table. The second column of the table contains the first 20 symbols of the wiki page text. As you have possibly guessed, this result is achieved using the getRange query. You can find the Python code performing such queries at class index. In the code, we make a cycle that processes titles we received earlier using the keys query and make a getRange query for each text value of each wiki page. As a result, we have a list of wiki page class instances, each of which stores the title and short text of the page to be displayed on the main page of the application. So far, you have learned how to work with strings, and this knowledge has already helped us to create a simple wiki application. If you are familiar with Python, you are free to experiment by extending the application, for example by adding page editing functions or adding the processing of some wiki language such as Markdown. Well, if not, that's not a problem. We can move on to the last video of the section, implementing cache using Redis. In the previous videos, we created the simplest wiki application using only basic Redis commands that operate on the keys and string values. When Redis began increasing in popularity, its main use cases were ending up almost totally with the implementation of some kind of cache. So let's see how Redis can be used in our wiki application to implement a cache. First of all, cache is a result of some calculations that can be saved somewhere and used. There's an important feature of cached values: they're eventually expired, either based on some lifetime or on some condition. Building cache on some condition requires coding. In this case, the cached value lives until the client makes a request to reset or remove the cache value, which is called cache invalidation. On the other hand, cache values can have an expiration time. This then deletes the key in Redis. In the first case, we have to code our conditions manually, and in the second case, Redis provides expiration facilities which implement the expiration of keys on the server. Let's start with the expired keys. Every key in Redis has expiration time. Everything we did earlier just meant that the keys we were setting are never expired, so their expiration time is infinite. There are plenty of commands working with the expiration of keys, but let's start with three major ones. Expire, which sets the expiration time for the key, TTL, which returns the expiration time for the key, and persist, which makes the expiration time infinite for a key. Now let's practice. Let's type set x1 and then expire x10, which will force the x key to be removed in 10 seconds. Then continue querying getX until the X key is removed to see the result. Now you can repeat the previous experiment except that use TTLX instead of get, which returns how much time in seconds the key has to live. The last command that we will talk about is persist. After you've set the expiration time on the key, you can remove this time by making the key persistent again using the persist command. So let's perform our experiment for the third time, except that we will use persist this time. As you can see, the last TTL query returned -1, which means that the expiration time is infinite for the key, so the key is persistent now. There are other commands that work with expiration: pttl, expire at, pexpire, pexpire at, which mimic TTL and expire but accept different kinds of arguments. Just visit the Commands tab at Redis.io to get more information on these commands. Let's return to our application for the last time to show how can we add cache to it. It is obvious that cache is used for data fetching queries. So let's look at the root page implemented in class index. We have to perform as many queries as there are pages created in our wiki. This can be harmful for our database. So it would be wise to cache the whole HTML code of our web page and invalidate the cache conditionally every time we add a new page or delete it from our wiki. This way, we save a lot of resources by replacing a bunch of queries with a single one. In order to check the cache of our index page, we can type get cache:index in our command line client. At this point, we have finished the first section of building databases with Redis. So far, you have learned how to build the Redis toolset, how to run the Redis server, and how to use command line client to connect to the server and perform commands on it. You also learned how to operate with keys and values, and you learned all you have to know about manipulating the string values and keys expiration time. There were also commands that we didn't discuss directly, so I recommend that you refer to the Commands tab at Redis.io and find time to experiment with those commands. At this moment, we are moving to the next section in which we will discuss basics of administration and security of the Redis database server. Welcome to the second section of the Building Databases with Redis video course. We will devote this section to the administration and security of Redis servers. In this section, we will discuss the basics of the Redis server administration and some main ways to provide security for the Redis server. There are basically three ways to change the Redis server configuration parameters. The redis.conf file, which is loaded when the server starts, and has some default options if you don't touch it. Passing options via command line arguments. In this case, the options are the same as in the configuration file, prefixed by 2 hyphens. And using Redis configuration commands. It is worth mentioning that these three ways have incremental priority, so the command line arguments have higher priority than configuration files. the Redis commands on the live server rewrite the previous configuration values. Let's start by exploring the first way of Redis server configuration, the redis.conf configuration file. If you have built the Redis project from source, as we did in the previous section, you can find the redis.conf file in the root folder of the project. If not, look through the documentation provided by the binary package maintainer. Now let's open the file and look through its content. We won't discuss all the options in this video, but the file is pretty self-documenting, using commentary lines that are prefixed with the hash character. We'll also discuss some of the options in the future videos. The configuration file format is pretty simple. Non-commentary and not blank lines consist of the option name and option value separated by a space. So, when you change some settings, you have to restart the Redis server for the updated configuration to be applied. Let's change the port to 6378, which the server listens to, and restart our server. As you can see in the terminal, the server still listens the old port. It happens because the configuration file was not specified directly in the command line arguments, so all options are set to default ones. So let's run the Redis server binary by passing an additional command line argument /redis.conf. Look at the last line of the output. The port is now set to the new value. Now we have to restart the Redis CLI command line client in order to specify the newly set port number using the -p option. It leads us to success. You can also use the --help option either by running Redis server or Redis CLI to see all the options that are accepted by those binaries, with sufficient documentation on them. That's all on configuring Redis from a file. Let's continue with our newly configured Redis instance that is running. The next way to configure the Redis server instance is to set options using command line arguments. In order to override some option, you have to use this option with a name specified in redis.conf, prefixed with 2 hyphens as a command line argument to the Redis server binary. Let's try to run the Redis server instance with the port other than the default one, while at the same time not specifying the configuration file. As you can see from the last line of the output, the port was set correctly. The same is true for any option you find inside the sample redis.conf file we were looking through earlier. The last way to configure the Redis server is to use the Redis configuration commands. There are 2 symmetric commands, config set and config get. They are used to set and get configuration options respectively. The most fascinating commands are those that modify Redis parameters on the fly. Let's try the same experiment with a change in port. First of all, let's get the port's value with config get port. Well, it's 6378 as we specified via the command line. Now, let's try to change it with config set port 6379. So what do we have? An error. This is very logical because the change in port will make all clients disconnect, and it generally does not make sense to change this option on the fly. So let's try to change the length of the slow commands log with config set slowlog-max-len 10. It says OK. You can use your knowledge now to get the option in order to ensure that the value was really set. It is cool to change the settings on the server on the fly, but if you use your custom redis.conf file when starting the Redis server, the options set by the config set command will be lost after server stops or restart. So you must directly tell the server to persist these changes to the configuration file. Fortunately, Redis has such a possibility covered by providing the config rewrite command. Let's execute the command in the client. An error again! Remember that we have started our server instance for the last time not specifying the configuration file, and the server tells us about this. You are free to experiment a bit. Try to run the Redis server configured from a file and persist an option the way we have discussed. That's all on configuration. We will return to some configuration options in the future sections and videos, as it is required to change configuration in order to turn on some of Redis features. Now we are ready to move to security topics, so in the next video we will discuss authentication. In the previous video, we spoke about the Redis configuration system. What parameters does the Redis server have, and the ways these parameters can be changed, either on the fly or when requiring a restart. This video is devoted to Redis authentication, which is rather simple. Configuration of server authentication is done totally via Redis configuration mechanism. Redis supports only one type of authentication, password-based. It is worth noting that this password is stored in a configuration file in plain text under the Require Pass option. Running a bit forward, it is worth mentioning that Redis supports master-slave replication, and this requires the slaves to connect to master servers, which can also be password protected. Use the master auth option to set the password for the master server. So now that you have an idea of how configuration is done in Redis, which was the topic of discussion for the previous video, you're able to change the password for the server in different ways. For simplicity, let's change the password for mysuperpass by typing config set require pass mysuperpass, and then try to perform a command, for example set x1. We will receive an error in which the server kindly asks us to authenticate first. The authentication is done with the auth command, which accepts one mandatory argument, the actual password. So let's type auth password. The answer is OK, which means that we have successfully authenticated. Now let's try to repeat the set x1 command. Everything works like a charm. As you can see, Redis authentication mechanisms are more than weak, and the best you can do here is use a password that is as long and complex as you can think. This leads us to the next thought. It will be better if you do not provide direct access to Redis via the internet. You don't have a trusted mechanism to provide good enough security, so you have to solve this problem using administrative solutions. The simplest solution is to encrypt traffic by setting up the SSL proxy between the client and server to be ensured that your traffic is not sniffed and no one intercepts your data. That's all on authentication, but authentication is not the only security consideration. So for now, let's move to the next video that discusses the login and monitoring capabilities of the Redis database server. In the previous video, we managed to set up a password-based security protection for our Redis server, and we also saw how such protection can be strengthened using an SSL encrypted connection. This video is devoted to two close topics, logging and monitoring. Logging and monitoring are possibly two of the most often used and important features that every server system must provide in order to ease the system administrators' lives. Such capabilities help to always keep track of what's going on the server and quickly react according to problems as they appear. Let's start with the way of getting information and statistics of the server instance. Redis provides the info command that retrieves and shows the information on a specific Redis instance. Let's open our command line client and type info. As you can see, it outputs a big mess of the information, which is separated into the following blocks. Server. This keeps technical information about the server software. Clients. This provides information on the connected client. Memory. This represents the memory usage statistics. Persistence. This shows the configuration and state of the storage, and we will discuss Redis storage in the next video. Stats. This refers to the block server primarily for statistics connected with connections and queries. Replication. This shows the current Redis instance replication setting. CPU. This shows the CPU usage statistics. Cluster. This shows the stats on the Redis cluster subsystem. And key space. This shows the average number of database keys. We won't go deep into every single value that is shown in this big information list. It's pretty easy to understand all the statistics once you know to which section it belongs. There is one important thing about statistics in Redis. Most of its values are aggregated as server instance works. Sometimes, possibly when the average load has increased or after some problem was fixed, it is worth clearing these numbers and running the statistics from the very beginning. Fortunately, Redis has the config reset_stat command that does the job. Look again through the output of the info command and then type config reset_stat and the info command again. Try to figure out what positions of the info command output were affected by the reset_stat subcommand of the config command. Let's finish with the server statistics and move on to the more interesting topic, real-time activity monitoring. It is provided by the monitor command, which basically writes all commands that are performed by clients on the server to the connection that initiated the monitor command. Let's make an experiment and open a new command line client to begin with. In this client, when we type monitor, we can see that the terminal has stopped working and there is no prompt. Let's now move back to our previous client connection and execute some command, for example, set x1. Now again, move to the client where we monitor the server. As you can see, a logit command has appeared. Monitor is very convenient to see all server instance activities in real time. However, it has one drawback. If the server is under high load, a lot of bandwidth is used to push all the login to the monitoring client. The situation becomes more complex when there is more than one monitoring client. Monitoring can be used not only for manual use, but also to create supportive tools for the development of some other facilities that make some statistical processing of commands and are not presented by the info command. And the last topic in this video is logging. By default, logging is done at the least verbose level and goes to the standard output. So let's move to the terminal where we started the server, where we see the actual log. You can configure the login settings in the redis.conf configuration file we were talking about in the previous videos via two options. Log level option, which can be one of the following options sorted in the descending order of verbosity: debug, verbose, notice, and warning, and the log file option, in which you can enter the path of the log file. There's also a possibility to use the syslog facility, usually available on Unix systems. It can be configured by setting the options prefixed with the syslog's prefix in order to enable syslog and set the current server syslog identity and facility name. The last type of login Redis supports is slow log, which stores the last slow queries. It is also configured via the redis.conf file or config command. First of all, you define what time of command execution is considered to be slow by setting the slow log slower than option in microseconds, and then you have to set up the slow log max len option, which defines the amount of log records in this log. Try to experiment with very low time numbers and make some queries. Then you can check a list of slow queries using the slow log get command. You can also get the length of a log with the slowloglen command and clear this log with the slowlogreset command. That's all on logging. Actually, Redis login facilities are extremely easy to set up and get access to. At the same time, Redis logging is powerful and performs possibly 99% of what the system administrator or developer expects from logging. Now, let's move to the last video of the current section, in which we will discuss Redis storage, how it is organized, and what Redis commands are used to interact with it. In the previous video, we spoke about monitoring and logging. This video is devoted to Redis storage. So we will discuss ways to persistence that Redis provides and their advantages and disadvantages. Redis does all its command processing in memory. This is one of the reasons why Redis is so fast in executing queries. In order to make data persistent, the server writes data to files. There are two kinds of persistency that Redis supports: RDB, which stands for Redis Database, and AOF, which stands for Append Only File. Let's start with the first one. The RDB persistent storage is based on saving point-in-time snapshot of the data onto the disk. The process can be performed either synchronously or asynchronously. This kind of storage is enabled by default and has certain advantages. The RDB file is rather compact. The rewrites of this file are safe. It provides a fast server restart. It can be easily used for data recovery, being a single file for transfer. At the same time, RDB persistence has the following drawbacks. Writing an RDB file requires Redis instance process forking. It is not good if you want to minimize data loss in the case of disaster. The process of writing RDB files is called snapshotting and is configurable via the Save option that can have multiple entries. This option receives two arguments: period of snapshotting in seconds and number of changes that trigger snapshotting. If either one of these conditions is met, snapshotting process is started. You can also trigger snapshotting manually using the Save command, which performs snapshotting synchronously, or the bgsave command, which performs snapshotting asynchronously. It is worth mentioning that RDB is more dependent on the available memory than an AOF. Another kind of persistency is called the AOF persistency. The difference is that it is not a snapshot that is stored on disk, but a sequence of changes, similar to what you receive after executing the monitor command. When you restart the server, this file is replayed, so it takes time to restore the in-memory storage. The advantages of the AOF storage type are as follows: higher level of data durability, which is gained by the possibility of frequent flushing changes onto disk; higher level of data security on power disaster or system crash. AOF files are append only. An AOF file can serve a log till the time it is storage. Though it provides certain advantages, it has also its disadvantages, which are as follows. It takes a long time for the server to restart. Replaying changes take time, especially on large databases. AOF slows down the Redis server more severely than RDB does. AOF is known to be buggy in the past. This kind of storage can be turned on in the configuration file with the append only option set to yes. The file path is configured via the append file name option. Similar to RDB storage type, there are commands to initiate AOF storage on the fly. One such command is bgWriteAOF. There is no synchronous analog because this kind of persistence is asynchronous in its nature using fsync. You are free to experiment. Try to initiate the AOF mode, make some commands, and inspect the resulting AOF storage file. For every project you will be developing or administering using Redis database, you will always have a question: what kind of storage to choose? Well, you have to analyze your needs, knowing the specifics of these storage types and then choosing what fits your needs best. The choice is individual for each case and can even change as the project evolves. At this point, we finish our discussion on Redis administration. In this section, we discussed the basics of administration and security connected with the Redis database server. We discussed ways to configure the Redis server, ways to set up logging and monitoring, and ways to deal with persistency. In the next section, we will return to the database design problems. We will discuss two other data types that Redis supports: lists and hashes. We will also see how they help in implementing a more complex application, an image gallery sharing web app. Welcome to the third section of the Building Databases with Redis video course, in which we will discuss such data types as lists and hashes. From this video, we will drop our wiki application development, which means we don't need the code and data from the previous sections anymore. We will start with a new application called Image Gallery Application. So let's start discussing the application step by step from the position of the user. In modern social applications, the login screen is usually the first thing that the user encounters when they begin using the app. So let's start designing a simple login password-based authentication system. First of all, every user stored in the database must have their unique unchangeable identifier. For example, login is not enough if the user desires to change it in future. All other users' data should be bound to that unique ID. At the same time, we need a mapping of login to the ID to find the user's data when authenticating. Let's start by organizing the identifier. Some database systems offer convenient means to organize unique identifiers. For example, relational databases have auto-increment integer fields, and others, such as MongoDB, create unique identifiers for stored objects automatically for each object. Unfortunately, Redis does not have such facilities, but at the same time, the task of generating unique IDs is quite doable. Let's recall the atomic counters we were talking about earlier, particularly the incr command, which increases the integer value stored with the specified key by 1 atomically and returns the result of such addition. It appears that we can use the behavior of the incr command to generate a unique ID each time we want to save information about some object in the database, and any conflict between the concurrent clients is excluded. Let's move on with the data structures design for our new application. First of all, when we authenticate into an application, we provide the login, and the server searches for the ID and then all the related data by the login. So obviously, we have to store a login to the ID mapping in the database with a complex key, for example, user to login ID: ID. Next, we have to store the login and password in such a way that they are queryable by the ID, so that other compound keys appear, such as user:ID:2:login and user:ID:2:password. Moving on. What if we want more fields such as date of birth and current status? Well, we will add more fields. Here the problems begin. The more fields we add, the more queries we will make later to show, for example, the user's profile page. Thus, making 20 queries to the database to receive 20 fields of one object does not seem very clear. So here we will discover the first limitations of our current approach. The first, we use as many queries as there are fields in an object to get object-bound data from the database, which slows down the application a lot. and the second, we use long compound keys such as user:id:2:login. All these strings take a lot of disk space, which is not effective. Redis offers a better way to solve the problem, the usage of the hash data type. This leads us to the next video, in which we will discuss how to use hashes to store object fields stored in one Redis key. At the same time, we saw the situation where using only string leads to dramatic performance and storage penalties. In the previous video, we tried designing an authentication system storage for our application using strings, but we have obviously failed to make it effective enough. In this video, you will learn how to make an efficient storage for user objects in Redis using the hash data type. Let's recall that Redis itself is a big hash table. However, Redis also allows us to store nested hashes. The only difference is that the values for such hashes can be string only. Still, it's enough for our task. Commands to work with hashes are very similar to those we have been using for strings, but they are prefixed with the H letter. Let's start by inserting hashes into Redis. The hash value is created when the first key-value pair was added to it, which can be performed either with the hset, hmset, or hset and x command. First, look at the login to ID mapping. We can use the hash data type here. So, for our database, we will store login to ID mapping in the users key, where the value type is a hash and where the keys are logins and the values are IDs. Let's add the mapping of the Rostislav login to ID1 with hset. The terminal shows 1, which means that the operation was successful. It can happen that someone would like to register the same login as the one existing in the database, so we need to set the key-value mapping if and only if one does not exist. Let's make the same query, but using the hset and x command instead of hset. The server answers with 0, no update was done. The last command that updates instances of the hash data type is hmset, which allows us to set several key-value pairs for one topmost key. It is not very useful for users mapping, because one won't insert several users at a time. However, at the same time, it is useful to add all information fields to store data about user with one query. One would mention that there are cases when this is not true, and we need to insert a bunch of users at a time, for example, when importing data on users from another database. In this specific case, hmset is the way to go. So, let's add information about a user with hmset with ID 1. We type hmset user:1 login Rostislav, date of birth 09.0h.1999, password secret, status happy. Okay, that's what the server answers. All key-value pairs were set successfully. The next big thing that would be logical to learn is how to get the data we inserted earlier. 3 commands can help use here. hget, which gets value for one key from the hash, hmget, which returns several values for several keys, and hmgetAll, which returns all keys and values from the hash. It's up to you which command to use, but the main criterion is to minimize the number of requests to Redis. For example, let's take the ID of our user. We type hget users Rostislav, and we get its ID, which is equal to 1. Next, we would like to receive information on a user, for example, to display its data on the profile page of our image gallery application. For this, we type hgetAll user:1. As you can see, we received a list of data in which odd entries represent keys and even entries represent values of the specified hash data type instance. If the returned data is more than you want, you can use the hkeys or hvals command to retrieve keys or values of the hash table separately. Let's type hkeys users and hvals users. As you can see, the result is Rostislav and 1 as expected. The last thing to learn about hashes is how to delete key-value pairs. You can of course delete the whole hash table with the del command from the previous section. However, if you want to delete one or more key-value pairs, use the hdel command that also specifies the key that represents the hash table and the list of keys to delete from that hash table. Let's type hdel users Rostislav. The server answers with 1 and then hget all users to see that the hash table is empty now. Now, when we know how to operate with hashes, let's open section 3/gallery.py to see how it is done via Python programming language. First, we will refer to the user class and the save method, which is started by receiving a unique ID using the atomic counter. Then, we will add a new user to the user's hash. Also, we will use hmset to insert all fields for the user object into a mapping with one query in order to minimize the number of queries to the database. Now, let's move to the loadWithLogin method of the user class, which is used to retrieve the user from the database by login. This method is used during the authentication process. First, we will use hget to get the user's ID and then hgetAll to receive all fields of the user's object. You can also see the login and register classes, which themselves implement authentication and registration procedures. That's all for this video. Now, we will move to the next video in order to learn how to deal with lists, another complex data type that Redis supports. In the previous video, we discussed hashes, a complex data type that allows us to store key-value pairs stored with one topmost key. In this video, we will continue discussing Redis data types by talking about lists. So, list is just an ordered sequence of string values. A Redis database allows to read, write, and delete values to and from lists. Returning to our image gallery application, we have to now think about how to store users' image galleries. We also need to think about what kind of queries we will do according to the gallery's data storage. First of all, we need to be able to show all galleries to the user. We could remember all we know about strings and hashes, and we could build gallery storage based on those data types, but it appears that the list data type fits our needs better. Let's begin by inserting list data into the database. Lists are also stored with keys because we remember that topmost Redis database structure is a hash map itself. We have several commands that allow us to insert data organized as lists into Redis: linsert, lpush, lset, and rpush. Actually, all list-related commands start either with the L or R letter. If the command starts with R, the operation deals with the end of the list, also called the tail of a list. Otherwise, the command starts with L, also called the head of a list. Let's try to create a list using lpush. It takes a key as an argument and a list of values to be added to the list. So we type lpush mylist 12345 in the command line, and the server returns 5, the length of the resulting list. Let's try the command again to add more elements. lpush mylist 67. The server responds with 7 as expected. You also need to remember that lpush prepends a value and not appends it. In order to append values to a list, you have to use rpush. which receives the same kind and number of arguments. So we will type rpush mylist 89, and the server will respond with 9 as it did with lpush. The next way to add data to list is linsert, which, unlike the previous commands, inserts values into the middle of the list. It takes a key, either the before or after keyword, and then the index of an element where we insert values. Finally, we will add a value to insert. Let's insert two values into the list after the second element. For this, we will type linsert mylist after 210. The last command that we will discuss here is lset. Unlike the previous commands, it does not add values to the list, but modifies those that were added earlier. The syntax of the command is the lset key index value. Let's change the first value of our list by typing lset mylist 000. The server responds with OK, which means the operation was successful. Now, when we know how to add and modify the elements of the list, let's look at how we can retrieve data stored in lists from the database. The most basic command to read data stored in a list is the lindex command that accepts the key and index values and returns a value stored at that index. Let's try the lindex mylist0 command that has to return 100 back. This is true. The server responds with 100. If we would specify a non-existence index, we would have received nothing for a response. Another command to read data from lists is lrange, which allows us to get more than one element at a time. It takes a key, start and stop indices, and returns a range of values. Let's type lrange mylist05 to get the first 6 elements of the list. Getting ranges instead of making several requests for single elements is a good optimization. Sometimes it's also useful to get the whole list of values. For this, we have to know the length of the list, which can be found out using the len command. Let's type len mylist to get the length of my list. The server says that the length is 10, and now we will type lrange mylist09 to get the whole list. Along with positive values, lrange can receive negative values for indices, which means counting indices from the tail of the list. So, for example, to get the whole list, you can omit using len and type lrange mylist0-1 instead. Quite an efficient hack. The last topic to discuss in this video is how to remove elements from lists. The first two commands that remove one value from lists, either from the head first element or from the tail last element of the lists, are lpop and rpop. Both commands return a popped value to you. Another command to remove elements from lists is lrem. It takes the key, count, and value parameters. lrem basically scans the specified list and removes the number of occurrences of the value parameter that is equal to the count parameter. Count can be either positive, negative, or equal to 0. When the count is positive, lrem scans the list from left-hand side and from the right-hand side if opposite. If count equals to 0, all occurrences of the value are removed. Let's type lrem mylist03 to remove all elements from my list equal to 3. The server responds with 1, which means that one entry of the string 3 was removed from my list. That's all on operations with lists. So let's move to the next video, in which we will inspect our image gallery application, particularly looking at a list of galleries and other practical applications of the commands you learned in this video. In the previous video, you learned how to deal with lists, particularly adding, modifying, reading, and removing values from lists. This video is devoted to practical tasks, namely design storage for galleries, implementing galleries pagination, and server history. Let's start with the galleries. We will display galleries on the main page of an application. Obviously, we would like to show all galleries that the user has created during the time of application usage. We can design the gallery storage in a manner similar to how we did with users. First, we have a field that stores the unique ID generator to generate gallery identifiers called nextGalleryID. Next, we will have each gallery's information stored inside a hash on a compound key gallery:galleryID. The last thing is to bind galleries to user, which we will implement through a compound key gallery:user:userID, which will store a list of galleries IDs for the user. Let's move to more practical tasks. Now that we are ready for the storage design, the first task is to display all galleries. As you have possibly guessed, the simplest way to get all galleries for a user is to execute the lrange gallery:user:userID 0-1 command to get all IDs and then iterate over the received galleries to get information for each gallery. So with this command we can receive a list of all galleries to display on the main page of our application. An interesting thing comes out when the user has a lot of galleries, 50 or more, which can be harmful not only for the appearance and user experience, but also for the database to perform 50 queries on each index page load. Unfortunately, we don't know for now how to optimize such sequences of queries, so we will try to hack this problem in another way. This way is called pagination, and you can find it in a lot of popular applications, either having pages control that allows to switch display pages, or in the form of a ribbon that loads portions of data, such as Facebook newsfeed does. Here, in the code of the index class get method, you can see how we get the number of pages through the given current page and count of galleries per page inputs. Calculations are pretty simple, so we won't discuss them in detail. In such a simple way, we decrease the number of queries per page load using the same storage design, while at the same time learning how to implement one of the most popular features of the applications, pagination. Another interesting thing that lists can be used for is surfing history, which is often represented as the so-called breadcrumbs ribbon in an application. Lists allow us to implement this logic pretty easily. First, when we visit some page, we just execute the rpush command with a link to follow. We can display this list using the lrange command, passing the 0 and -1 parameters as range setting. When we decide to roll back our activities by clicking on the back link, we perform the opposite command called rpop, which removes one element from the list's tail and returns it to us. It is also simple to return several steps back using the lram command. In such a manner, each action that we perform with a surfing history costs only one query to Redis, which is quite efficient and blazing fast. At this point, we are done with the lists. We are now ready to move to the next section, which is devoted to the last but not the least important Redis data types, sets and sorted sets. Now we start the fourth section of the Building Databases with Redis video course. In the previous sections, we discussed string, list, and hash data types, along with basic administration and usage tools. In this section, we're going to talk about sets and related data types, that is, sorted sets and hyperlog-log, a set organized using a special algorithm. This video of the section is devoted to sets. Let's define what set is. A set is an unordered sequence of strings. That means on one hand it is a container of elements, just like list, and on the other hand Elements of a set do not have a specific order, so they don't have indices. This leads us to following conclusions. We can add elements to set, read a set as a whole, or check whether a string is a part of a set. That's all for theory. Let's move to the practice. The first thing we're going to discuss for sets is how to create sets by adding elements to them. As was said before, a set does not have specific order, so there's only one command that adds an element to a set, sadd. This command receives a key on which new or existing set is stored, and at least one string that is going to be added to set. Let's add 3 elements to set by typing sadd myNumbers 1, 2, 3. The server answers with 3, which is the number of elements added to set. Elements in set are unique strings, so we cannot keep a string twice in a set. It is easily checked with the sadd command. Let's type sadd myNumber1 set to ensure that server's answer is 0. Also, you can check the number of elements, which is also called cardinality, of a set with the scard command, which stands for set cardinality. Here, when we type scard myNumbers, the server answers with 3. Now, let's discuss removing element. The first way to remove elements is an srem command, which accepts a key and at least one string to remove from set and returns number of items removed by the command. Let's remove one element from the set with srem myNumbers1. Then we can type scard myNumbers in order to see that there are only 2 elements left in the set. Another way of removing elements from a set is the spop command. This interesting command removes one random element from the set and returns it to the client. It takes only one argument, a key on which the set is stored. Let's try it on our set myNumbers by typing spop myNumbers. As you can see, the element was removed from the set. The next thing to discuss is reading data from sets. As there is no order of elements in Redis sets, it is obvious that we cannot get range of elements or get elements by index like we did with lists. The only things we can do is either to check whether some string is a member of a specific set, get some random elements from set, or read a set as a whole. Let's start with the first one. We can use the sIsMember command in order to check whether a string is a member of a set by specifying a key on which the set is stored, and an element on which the membership is checked. First of all, let's add some more elements to our set. Now we try 2 cases, when element is member and when it is not. For that, we type sIsMember myNumbers5 and sIsMember myNumbers10, receiving negative result in the first case, 0 means false, and positive result in the second case, 1 means true. The next command we are going to discuss is sRandMember, which accepts a key and a number of elements to return, and return that specified number of random elements from set. So we type sRandMember myNumbers2, and we get 2 random elements. Take into account that your answers may be different here. The last thing on reading data stored in sets is to read the whole set of elements, which is done by using the smembers command, which accepts only one argument, the key. Also, be careful with the command, because returning large set of results can cause a big cost on the performance. Let's take all members of our set by typing smembers myNumbers. As you can see, all members of our set are printed in the terminal. Now, let's get even more practical and take a look on a real task, creating a text cloud for the image gallery application we were working with in the previous section. Also, in this section, you won't find code that inserts data into Redis in Python examples, only the code for reading data and displaying it inside application is present here. So, you will have to get some practice adding data into database from Redis command line client manually and watch the results. So, A tag is a text string that somehow identifies the image gallery. For example, if you store city photos in a gallery, you can tag your gallery with strings such as buildings, lights, city, urban, and so on. Obviously, you don't want to use two equal strings for tags in one gallery, and that's why sets are an ideal way to store gallery tags. For our application, we can use compound key gallery colon tags colon gallery ID, which will store the set tags. You can check out the code in the save and load with GID methods of the gallery class in our application code. These methods execute the sadd and smembers commands in order to add elements to set and to get whole elements from set respectively. Such storages allow us to easily retrieve text from the Redis database and display those somewhere along with image gallery representation on the web page. That's all for sets in Redis, the best data type to use for storing sequences of unique strings in database. Now, we are ready to move to the next video, in which we will talk about another kind of sets called sorted sets. In the previous video, we were talking about sets, and this video is devoted to sorted sets, which mostly behave like ordinary sets, but whose elements have two more properties: index and score. Unlike ordinary sets, elements in sorted sets are ordered, but each element is unique throughout the whole set. As you have possibly guessed, an index is a position of an element in sorted set like we had in list. At the same time, a score is a criterion on which elements are sorted. Thus, the lower the score of an element, the lesser index it has in a sorted set. Let's start discussing sets like we did all the previous times while adding elements to a sorted set. You can add elements to sorted set with the zadd command, which accepts the key and pairs of score and value to insert into the set. Let's type zadd sset112233 to add three strings 1, 2, and 3 with scores corresponding to their integer values. We can check the cardinality of the sorted set with the zcard command specifying the appropriate key. Here we type zcard set and receive 3, and that's alright because right before we have added 3 elements to set. Removing elements from set is even simpler. The command is pretty the same as in case of ordinary sets. Instead of it starts with Z character, not with S. So let's type zram set123 and then zcard set, and the server replies with 0 as expected. Currently, there are no elements in our sorted set. Let's move on and try to read data from sorted set. Like in case of ordinary sets, you have two types of commands, checking and reading. You can check either element by score or by rank, which corresponds to index. In order to get element score, we will use zscore, and zrank is to get the index. Both the commands accept the key and the element value. Let's return to our set and fill it with values again, typing zadd set11223344. Now we play with the 4 value. Let's get the index and score of the value by typing zscore set4 and zrank set4 respectively. The server answers with 4 and 3, which tells us that the rank is 4 and the index is 3, as indices are starting from 0 in Redis. That's all for checking commands. Now let's talk about reading elements from sets. There are 3 ways to get ranges of elements from sorted sets: by score, by index, and by lexicographical order. We start with getting ranges by score. It is possible with the asRangeByScore command, which accepts the key, the minimal score, and the maximal score value as arguments. Minimal and maximal values can be either integer values prefixed with left bracket, that means that the interval is exclusive, or -inf and +inf special values that mean negative and positive infinity respectively. So let's take all values of our set sorted by score, type in zrange by score as set -inf +inf. In order to get the first two elements by score, we can type zrange by score as set -inf2 or zrange by score as set -inf left brace 3. In the last example, 3 is exclusive, so the result is the same as in previous one. It is also possible to receive a result with scores by finishing the comment with the string with scores, which will tell Redis to return not only values, but also their scores. Let's try it and see the result. The next way to read data from sorted sets is zrange, which acts and accepts exactly the same arguments as lrange, which operates lists. So let's take first three elements from our set by index, type in zrange as set 0, 2, and then the whole set by typing zrange as set 0, -1. As with list, negative indices mean counting from the tail of the set. The last thing to know about reading data from sorted set is the lexicographical order. This kind of string comparison is based on comparison of strings character by character, which practically means that B is greater than A, AB is greater than AA, and so on. The interesting thing is that if elements in sorted set have equal score values, their rank or index is defined by ordering these elements lexicographically. You can read elements sorted in lexicographical order using zrange by lex command, specifying minimal and maximal values of strings to compare lexicographically. Also, remember that score is more important, so let's drop all elements scored to 0 by typing zadd as set 0, 1, 0, 2, 0, 3, 0, 4. The zrange by lex command receives the same set of arguments as zrange by score does, except it uses minus and plus instead of -inf and +int for infinity values. Also, you specify strings except of integers for minimal and maximal value. So let's try it on an example by receiving all strings sorted lexicographically between 2 and 4 exclusively by typing zrange by lex as set left brace 4, left brace 2. It is pretty enough to compare only first characters of our elements to see that we have received right result. It is worth mentioning that lexicographical order is very convenient and often used to create autocomplete widgets in web applications. Now, let's move back to our application and see how can be sorted sets used. In the previous video, we designed a tag storage for galleries. Now, let's talk about a tag cloud. A tag cloud is a set of tags for user that include all tags from all galleries. Those tags that appear more often are displayed with bigger font sizes and others as smaller font sizes. Well, now you can see that a sorted set is a pretty nice candidate to be used for a tag cloud design, so that the more times a tag appears in galleries, the higher the score this tag gets in a sorted set. Having knowledge of how to use the zrange by score command, we can easily build tags cloud for our website. You can inspect the loadWithUID method of the user class inside gallery.py module, where tags cloud is read from Redis for a user. The tags cloud is stored in a sorted set on a compound key user tags cloud scored user ID. At this point, we have finished discussing the most complex yet the most powerful and interesting data structure that Redis offers, sorted set. Working with Redis, you will find out that it is possible to use sorted sets efficiently in different situations where you have to store sorted sequences of unique elements. Now, we are ready to move to the next video in which we will discuss the last uncovered data type, hyperlog. In the previous video, we were talking about the sorted set data type, which basically extends the possibilities of ordinary sets by adding order to uniqueness of set elements. In this video, we are going to talk about another data type based on sets called hyperlog-log. Hyperlog-log is a kind of data type that is called probabilistic, which means, unlike deterministic data types, this data type can store elements with certain probability. The main purpose of the hyperlog-log data type, which is a set itself, is to tell the approximate number of unique elements in it. The point is that it uses far less disk space for storing elements than ordinary set. Let's start with adding elements to hyperlog-log. It can be done with pfadd command, which receives a key and a list of elements to be added to set. Let's try to add some elements by typing pfadd mylog123. The server replies with 1, which means that the data was updated successfully. Also, while this is not really a classical set, the pfadd command calls may return 0, while they would have to return 1 normally. Try to run pfadd mylog1 and you will see that the returned value is 0. It happens because hyperlog-log updates only when its cardinality is updated. In order to get number of elements, we can use the pfcount command, which accepts only one argument, the key of the hyperlog-log instance. Let's type pfcount mylog. As you can see, the answer is 3, which is true because the less elements are in the hyperlog-log, the more precisely the pfcount command works. The last command that is used to manipulate hyperlog-log is pfmerge, which merges two sets into one. It accepts the key that identifies the destination, and any amount of keys on which hyperlog-logs to be merged are stored. Let's create another set by typing pfadd mylog2 10, 11, 12, 13, 14. Now we type pfmerge mylog3 mylog2, and then we are ready to check mylog3 with the pfcount command. As you can see, the result is age, which is the exact number of elements we have added before. Now, let's talk about practice. When talking about web applications, hyperlog-log is often used to count unique visitors. It has small demands on storage, but still gives quite an accurate result. So the algorithm is pretty simple. When someone enters the web page you track, you call pfadd to add the specific user ID to the set which is kept for the specific page. After that, you can use pfcount in order to get the number of visitors. At the same time, it is possible to merge all hyperlog logs from all pages in order to receive overall visiting statistics for your application. At this point, you have learned everything about the usage of hyperlog-log data type in Redis, and we have covered all data types that Redis offers so far. So we are ready to move to the next video, in which we will return to ordinary sets, namely to operations on sets. In the previous video, we discussed the last data type we were to cover in our video course called hyperlog-log, which allows us to efficiently store large amounts of elements in a probabilistic set. This video is devoted to performing operations on sets. There are several classical mathematical operations done on sets: union, intersection, and subtraction. Each operation can include any operand number to operate on. In this video, we are going to talk about union operation. So the result of union operation on sets is a set that includes all elements of sets that are operand. Let's look at the example. First, we create two sets with the sadd command. Let's type sadd set1 1, 2, 3 for the first one, and sadd set2 2, 3, 4 for the second one. The sUnion operation performs the union of two sets and returns the result. Let's type sUnion set1 set2. As you can see, the result includes all elements from the set1 and the set2. There's another modification of the union command called sUnion store, which stores the result of the operation inside another key in Redis. Let's type sUnion store set3 set1 set2 and then use smembers set3 to see if it worked. As we can see on the screen, the result is the same as after S-union. At the same time, it is stored on the set3 key in Redis. Let's move to the practical application. In our gallery application, we worked with an example with cloud of text. For that, we have used sorted sets. Sometimes clouds are done without scoring, so there's no need to use sorted sets. Moreover, when we know how to perform the union operation, we can build a tag cloud using the sunion command from all sets of gallery tags and don't even store it inside the database. While this approach takes less disk space and memory, it is slower. So we can inspect the init method of the tag cloud class in order to see how unscored cloud can be built using Python. At this point, we have seen the union operation. At the same time, we discussed how unscored tag cloud can be built from sets of galleries tags using union operation. In the next video, we're going to finish discussing sets by covering another two operations on sets, intersection and subtraction. In the previous video, we were talking about operation on sets and union operation in particular. In this video, we're going to finish discussing sets operations by covering intersection and subtraction. Let's start with some practice. Every social application must implement some user-related logic. If our application needs to be social, it would be great if we had some mechanism to work with friends. We can implement friends as a set of user IDs stored on the user:friends:user ID compound key. Some popular social applications allow you to see friends in common if you visit your friend's profile. The intersection operation is something what will be useful to implement this logic. So, intersection is an operation on sets which result in the common elements between all sets. Let's create two sets by typing sadd user:friends:0 1 2 3 4 and sadd user:friends:1 0 4 5 6. These sets store friends for users with identifiers 0 and 1. The sinter command allows to perform intersection and thus finds friends in common. Let's type sinter user:friends:0 user:friends:1 and the result is 4, which means that those users has only one common friend with identifier 4. As with the union operation, intersection has modification that allows us to save the result into another resulting set. The operation is sinterstore. In our case, it can be used, for example, cache common friends. Let's type sinterstore user:friends:0:1 user:friends:0 user:friends:1 and then check the result with s-members user:friends:0:1. This works as expected. The last operation on sets is subtraction, which is implemented through the sdiff and sdiff-store commands. Subtraction, or difference, is an operation whose result is the elements of the first set that are not members of the second one. So we basically remove all elements from the first set if they appear to be in the second one. Thus, we can use this operation to find a user's friends contacts that are not user's friends and recommend user to make a friendship with them. Let's try with our created sets by typing sdiff user:friends:1 user:friends:0. As you can see, we received all friends of user 1 that are not friends of user 0, so we can recommend user 0 to make a friendship with those guys. At this point, we finished learning about sets along with sorted sets and hyperlog data type. We covered those complex data types and found out that there are many use cases when sets offer the best storage and can even be used to implement interesting logic without writing a single line of code. So, we have finished with the section 4 and are ready to set sail to the section 5, in which we are going to discuss publish-subscribe mechanism, a way to perform messaging via Redis. Welcome to the fifth section of the Building Databases with Redis video course. In the previous sections, we discussed all the data types that Redis allows us to operate in order to create efficient data storage for specific tasks and needs. In this relatively small section, we're going to discuss the publish-subscribe mechanism that is quite unique for database management systems because it is not directly related for storing data, but implements a messaging mechanism. In this section, we will be experimenting with database design for a chatting application, its architecture and data storage. In this video, we won't discuss any application code in order to place more stress on Redis itself. Well, eventually, this is a video course on Redis, not on Python. Let's start this video by depicting what we expect from the application. Firstly, it will be an anonymous chat with no authentication. Secondly, it will allow direct messaging between users. And finally, users can enter rooms more than one at a time. So this video we will devote to the discussion of data models based on our experience, knowledge gained from the previous section. The first model is the user model. We have stated that our chatting application won't require any authentication, so basically what we want is just to inform somehow that the user with specific nickname is entering the chat server. The simplest way is to store all users in a user set on server. Storing users that way will require the next operations. First, we use the asIsMember command to check if the user with the desired nickname is already registered. Let's type asIsMember users me. Then, if our nickname is available, we use the sadd command. Let's type sadd users me in order to register ourselves. The last thing we need is to unregister ourselves with the srem command when leaving the chat server. So finally, we type srem users me. This command's flow is the basis for our storage. While we don't have any security considerations for the chat application, such an organization of user model seems to be simple and great, with everything stored in one Redis set. Now let's move to how must we store messages. Obviously, there are three mandatory fields for messages: message body, message author, and the room in which the message was published. When talking about queries, messages that are stored in Redis can support retrieving communication history. Thus, we can only have one type of query which receives some portion of messages either for the room or for direct communication between two clients. For that, we can store messages in lists on compound keys which are similar to m:\room:\room name or m:\direct:\user1:user2. This list is nice because on one hand it helps us to preserve the messages order and allows the user to receive either all messages or some portion of them. The only thing we didn't implement here is authoring. Like we use compound strings for keys, we can also use compound strings for values, so our message will look like this: author::message. That's all on messages, and at this point we are ready to move on to having users and message data storages implemented. As you can see, storages are extremely simple and only minimal number of queries for common chatting application tasks is required. So, we are ready to move to the next video in which we will learn how to perform messaging itself using built-in Redis publish-subscribe mechanism. In the previous video, we were talking about storage for main models of the chatting application, but didn't say a word about actual messaging. Usually, databases are only associated with storage function, but Redis pushes the bounds and offers a mechanism for exchanging string messages between clients, the publish-subscribe mechanism. The central entity of the publish-subscribe mechanism is called a channel. In general, a channel is a key that is stored for routing messages from one client to another, though it's not a key in its classical sense, so you cannot get channels, for example, with the keys command. Clients interact between each other and Redis as a mediator through the channel using publish-subscribe. So the algorithm is pretty simple. One client uses the subscribe command in order to enter into listening mode. Subscribe takes one or more channel names or keys which the client would like to listen to. The other client uses the publish command, specifying the channel name to which message is published and message body. This command pushes a message from publisher through the Redis server to another client, which is subscribed to that specified channel. Channels are not for single usage, which means that any number of clients can either subscribe or publish to one channel at a time. You can subscribe to a channel using the subscribe command. The subscribe command receives as much number of channels as you need to subscribe to. Along with that, this command blocks any subsequent commands from current command line client until you press Ctrl+C in order to shut down the current session. Let's type subscribe my channel in order to initiate subscription. The server answers with 1, which means that we have successfully subscribed to a channel. At the same time, you'll notice that the command prompt has disappeared and the terminal is just waiting for the incoming messages. So let's continue and give those messages to the terminal. Now we need another command line client session in order to continue the experiment, and currently we are talking about publishing. Messages are published via the publish command, which accepts two arguments, channel and message to send through that channel. Let's use the channel we have previously subscribed to, called my channel. So here we type publish my channel message 1. If we return to the previous terminal, we will see that the message has successfully received. The output tells us that the message with the body message 1 came from the my channel channel. Let's move on. The last thing to do with our subscriptions is to cancel the subscription. Unfortunately, as was said before, the command line client blocks any subsequent commands in a connection after the subscribe command was called, so we can't achieve it with standard client, unlike what we can do in an application using the appropriate driver for our favorite programming language. However, we can use another utility called telnet in order to test how the unsubscribe command works. The unsubscribe command receives a list of channels to unsubscribe from. Let's run telnet in the terminal. Then we use the O localhost 6379 command in order to establish connection with the Redis server. Now we can send commands. First we type subscribe channel in order to initiate subscription, then we type unsubscribe channel and we see that it works. Now we can type quit in order to finish working with Redis. As you can see, the output is much worse than the standard Redis command line client provides, as telnet protocol is more general and shows us the output as is without any filtering or processing. That's all for sending direct messages. You can experiment by adding another two terminals with one subscription and one publishing client respectively. It appears that a chatting application client consists of two connections. One listens to channels and the other is used for publishing. Just think how beautiful the next phrase is. You can basically use only standard software in order to establish network communication without writing a single line of code with Redis. Now we can move to the next video of this section, in which we are going to discuss implementation of a chat room. In the previous video, we discussed how the publish-subscribe mechanism is used in Redis to exchange messages between clients. Now, we need to move on in implementing the steps described in the first video of this section, namely organizing rooms. So, a chat room is a group of users that are connected together the way that every user is able to see all messages sent by other users that are located in this specific chat room. In the first video of this section, we have discussed how our messages stored in the Redis database, and we have added room information as a part of the compound key. The rooms themselves do not necessarily need to be stored in database. It is enough to agree that a room corresponds to an open channel, and each user that is subscribed to that channel is automatically considered to be joined to the room. However, if you would like to show a list of users in a room, it would be wise to store users before subscribing to the room channel in some persistent storage. As each user is a unique entity from the room's point of view, we can store users in rooms as a set-on compound key room:"room name. So we type sadd room:"lobby me admin, for example, and it means that two users, me and admin, have entered the room called lobby. The same way as you add clients to rooms represented by sets, you have to remove users from rooms represented by sets when we unsubscribe from the channel. Logically, unsubscription means that the user leaves the room. Another interesting task is how to get a list of rooms available on server, especially because we haven't stated that we are storing rooms somewhere. The Redis server offers an interesting pub/sub command that allows us to inspect the publish-subscribe subsystem on the server. We can use the pub/sub channels subcommand to receive a list of channels on the current Redis server. This subcommand receives a pattern like other patterned commands do in order to filter the returned result. Let's type pub/sub channels *. We receive a list of channels that are currently opened on server. Another subcommand called pub/sub numsub receives a list of channels and returns a list of channel names and the number of subscribers for those channels respectively. Using these commands, you're able to receive not only a list of rooms for the chatting application, but a number of users in each room. The interesting part is to know what a chat client is. The chat client, as you could have guessed from the ending of the previous video, consists of two connections. The first is the connection that is subscribed to a channel, and the second is a connection that is used to publish messages. So, when you design your application, you have to keep in mind that the subscribe command is a blocking one, which means you need to either use non-blocking I/O API or design a threaded application in order to implement a chat with nice user experience. At this point, you have learned how to implement room storage, how to get information about rooms from database without actually storing them in database, and how to implement chat logic for messaging with room support based mostly on standard Redis database management system facilities. So let's move to the last video of this section, in which we will discuss multi-channel subscription. In the previous video, we discussed how to organize rooms in chat application. Along with that, some requirements to client application architecture were also highlighted. This video is devoted to multi-room support and pattern type of subscription to channels. When we discussed how to subscribe to channels, we were using only one channel as an argument, though subscribe command allows us to use any number of channels we like. Let's open a terminal and try to subscribe to two channels at a time by typing subscribe C1, C2. As we can see from the server's answer, we are now subscribed to two channels, C1 and C2. The integer values just mean number of channels this connection listens to. Now, we can move to another client and try to check whether the subscription really works by publishing messages into both these channels. Let's type two commands, publish C1 message 1 and publish C2 message 2. The output again shows us what channels we have received messages from. So, talking about our chat application, we can state that only two connections are still needed to implement a fully functional client and subscribe to several rooms at a time. Remember the first video of this section? We were talking about not only room messages, but also direct messages. Actually, such type of messages can be implemented similar to rooms, except that we will name channel after both names of users like we used those for compound keys in direct messages storage. Another way to perform subscription and unsubscription to several channels is to use the psubscribe and punsubscribe commands. Unlike subscribe and unsubscribe, these commands accept patterned channel name, such as in the keys command instead of exact names, and allows to subscribe and unsubscribe to those channels that match the pattern. Let's open a new command line client and use psubscribe in order to subscribe to existing C1 and C2 channels. For that, we type psubscribe C**. After that, we will receive all messages coming from channels whose keys start with the C character that is now demonstrated on screen. How can this be used in our chat application? Well, that's up to you. A lot of chat applications use their own protocols when sending messages on application level in order to perform some kind of automation or configurations. You can, for example, create utility rooms for such things starting with command prefix or so. That's all for the chat application and for the section as a whole. In this section, you learned how to work with the publish-subscribe messaging subsystem of the Redis database management system. And you also learned how can you use Redis to implement a fast, simple yet quite featured chatting application using mostly Redis built-in features. At this point, we are finished with the 5th section and we are ready to move forward to the 6th section, in which we are going to discuss replication and failover capabilities of the Redis servers and clusters. Welcome to the 6th section of the Building Databases with Redis video course. In the previous section, we finally finished exploring all the data types and queries related to data manipulation in Redis. In the second section, we started discussing administration tasks and learned basic possibilities and commands that Redis DBMS offers to system administrators. This section continues to examine the administrative part of Redis, although it also touches topics that are interesting to developers. Many of these questions are connected to scaling and high availability, involve some coding, especially when talking about horizontal partitioning. So let's start the first video of the section in which we are going to discuss master-slave replication. First of all, let's get clear about what scalability is. Scalability is a property of a database to handle a growing amount of queries and/or storage. Practically, it means that a scalable system can be adjusted to fit growing demands in queries load or storage. Master-slave replication is one of the ways to achieve scalability. The principle is very simple. You have at least two Redis servers, one of them is a master and others are slaves. All servers store the same copy of data through all databases. The difference between these kinds of servers is that slaves are read-only and the master accepts reads and writes. That means that such node stub is good when you have larger number of reads than writes. When data update happens on master, it eventually affects slaves, so all writes to master are distributed over slave Redis instances. That's about theory, and now we are ready to get closer to practice. In the real world, you usually set up masters and slaves all on different machines with separate storage devices. One of the advantages of the master-slave replication is that when one of your instances becomes corrupted, for example because of hard disk corruption, your data remains safe as a copy exists on other instances. For our experiments, we will run all Redis instances on one machine. After all, we are not doing production system right now. So, first of all, we have to start a fresh Redis instance which we will use as a master instance. For that, we type redis server --port 6379 --db file name db1.rdb, which starts Redis server for us. Next, let's raise up another instance, which we are going to use as a slave. For that, we type redis server --port 6380 --db file name db2.rdb. Now let's connect sequentially to both of the servers and enter keys * command in order to check that both databases are empty. At this point, we are ready to make the second Redis instance to be a slave of the first one. This is done easily with the slave-of command. This command accepts two arguments, host and port of the server, for which current instance is going to be slave. Let's enter slave-of localhost 6379 in order to create a master-slave cluster. The server replies with OK, which means the operation has finished successfully. If we move back to the first Redis instance tab, we can see that the process of accepting slave instance is accurately logged. Now it's time to see how the stuff works. Let's move to the Client tab, connect to the master instance, and insert a new string into database by typing set master:\key value. Check the key with get command. Now let's close our connection to master with quit command and connect to slave instance. If we type get master:\key, you can see that we receive value, though this key was not set on this instance. That is how master-slave mechanism works. Although if you type, for example, set slave:\key value in order to update data directly on slave, the slave will answer you with an error. And finally, if you have to break the master-slave connection between servers, you can use the same slave-of command with two constant strings no1 as parameters. Let's try it and type slave-of no1 while connected to slave, and it answers with OK. At the same time, the operation is logged in master instance terminal. That's all for master-slave replication on Redis. As we have seen through this video, it is extremely easy to set up master-slave mechanism and receive a scalable system. While having its advantages like simplicity, data security, and scalability over read queries, master-slave mechanism duplicates the usage of data storage and does not allow us to scale that storage. In contrast, storage scaling becomes efficient when we are talking about horizontal replication, and that is what we are going to discuss in the next video. In the previous video, we were discussing master-slave mechanism, the simplest way to add scalability to database storage implemented using Redis database. In this video, we are going to talk about horizontal partitioning, which is often called sharding. Horizontal partitioning is a database design principle which features database records stored separately in different database instances, usually hosted on separate physical servers. Each of these instances is called a shard. Since different shards are located at different physical locations, each single shard has a reduced number of records, which increases their processing speed. Also, sharding enables practically infinite number of Redis instances that can be spread over geographically distributed data centers over the world, easing customers' concerns with such kind of segmentation because customers become geographically closer to the data. There are two major approaches to sharding related to Redis: range partitioning and hash partitioning. Let's start with the range partitioning. This kind of partitioning means that all data is initially split into ranges that are held on reserved Redis instances. For example, when we have 1000 accounts in our application, we can say that first half of 1000 is stored at the first shard and the second half goes to the second one. This approach is the simplest one, but you have to understand that this kind of sharding is fully client-based and has no implementation on server. Let's explore the range.py Python script located inside sharding folder in the examples. The getShard function lines from 14 to 24 takes user ID and returns appropriate connection based on that user ID. In this simple example, first 500 users are saved to the first shard, all others go to the second one. The saveUser function determines what shard to use by calling getShard function and uses set command to store user's data to appropriate shard. And at least at the end of the script, we can see the actual scenario of the script. We define two users and then saving those to database. Looks pretty simple. Less than 50 lines of code with commands to implement sharding for us. Now let's go to the terminal and run the script by typing python./range.py. Also, don't forget that both Redis instances have to be up and running at the configuration we have left them in previous video. Now let's connect to both instances with Redis command line client and use keys command to check if everything worked as expected. As you can see, the user with ID 4 went to the first shard, and the user with ID 504 went to the second one. That's what we wanted to. The next way of sharding is based on hashes. Let's consider the same task we have implemented in Python using the range partitioning method. Hash partitioning requires the next steps. First, we have to design compound keys. User::id::id is good enough. Then we have to choose some calculation procedure, some hash function, for example crc32, in order to get numerical hash of that key. And the last thing to do is to make a modulo of the integer division on the number of shards we have. These steps are implemented in hash.py Python script in getShard function. The received number is a required shard. This kind of balancing does not require planning of ranges, just planning number of shards for our application. Now, if we move to the bottom of the script, we will find users we're going to save into our sharded database. Here we have users with IDs 1 and 4. Those are specially selected to balance records into two shards. For example, users with IDs 1 and 2 will both get to the first shard. Let's run the script and then check results of those scripts. You can also run flush all command on both databases in order to remove all the keys from them. As we can see, those records are divided between shards. At this point, we have found out how horizontal partitioning can be implemented for Redis databases. Along with its advantages, the horizontal partitioning approach also has its disadvantages. As you may have noticed, our data is not duplicated, so there is a risk of data to be lost. But fortunately, it can be easily fixed if you add master-slave setup to all your shards. Thus, if all shards have at least one slave, they're not only secured, but can use the master-slave mechanism to support any high loads or spikes in reading requests. Until this point, we have been doing replication manually, and though it is simple and appropriate code can be written in literally minutes, Redis also offers automatic replication with the Redis cluster utility we are going to discuss in the next video. In both previous videos of this section, we were talking about scalability and how scalability can be added to Redis database in order to resist growing loads in querying and storage. We have discussed two mechanisms, master-slave and sharding, their advantages and disadvantages, and how to combine them in order to design scalable database for an application. All we were working with before was done manually using either slave-off command or coding shards balancing procedures as a part of an application. In this video, we're going to continue talking about how both of those things can be set up to be done automatically, and the Redis cluster utility that comes with the latest development versions of Redis, and how to implement automating these scaling tasks. First of all, we have to state that Redis cluster, while already available, is still in an alpha stage of its development, so it is not recommended to be used in production environment. Redis cluster is still going to be the main way to scale your Redis database, and we are now going to discuss its main capabilities. Generally, you have two ways to acquire Redis cluster. First is to use Redis version 3, which is in release candidate for the moment of the video course is recorded, or download fresh Redis sources from GitHub and use the latest version of Redis and Redis cluster utility. As we are working with Redis version 3 already, we have Redis cluster already built and ready for use. The only thing the script needs to set up, configure and update cluster configuration is at least two Redis servers that are aware they are going to work within a cluster. For that, let's create two configuration files in some folder with minimal configuration for the Redis servers. Notice that we use two different ports which servers are going to listen to. Also, we have three new configuration options here, which include cluster enabled, which is set to yes and means that the node is a member of a cluster. Cluster config file, which is set to the node configuration file name, and cluster node timeout, which is used by cluster to specify how much time the socket will wait for writing changes to cluster node. Let's start the first server by specifying node1.conf as a configuration file. After the server started, notice the new label on the right of the Redis database logo telling running in cluster mode. And now the same for the second server in new terminal instance. Another thing that has happened without our influence, two files were created, cluster node1.conf and cluster node2.conf. These files are operated by nodes themselves and you are never supposed to edit them manually. Also, AOF files, which store actual database data, were also created for each node. Redis cluster is operated by the utility called Redis-stored, which is located in src folder of the Redis project along with other binaries. Redis-stored is a script written in Ruby which operates cluster. If you don't have Ruby interpreter installed, visit ruby-lang.org website, find instructions for your operating system and install Ruby. After that, you have to install Redis Ruby package using gem utility. So we type sudo gem install Redis, then enter password and wait while the installation is done. Now we are ready to run the cluster. Let's enter the directory with configuration files and use Redis-stored script passing command create and a list of servers involved in the cluster. We get an error. That is, Redis cluster utility does not allow us to create clusters with less than 3 servers, while you can shard your data into 2 servers manually. Okay, so let's add one more server with configuration and run it. Now let's repeat cluster creation procedure. Redis-stored utility asks us if we want to save current configuration. Let's type yes, and here it is. The cluster is created, everything is okay. Now it is possible to work with cluster. Let's connect using Redis command line client to any of our instances, for example localhost :7000. Here we must also pass -c command line option in order to tell server we're working with cluster. Now we can use ordinary Redis commands. Let's try zx1. Here the server says the key is saved at server with port 7002. Let's type next commands zy2, setz3. So Y key is stored at the same shard and the Z key was redirected to 7001. Congratulations, the cluster is working. It is also possible to define master-slave replication for each of the shards by passing --replicas count option, but you have to remember that if you want to have, for example, one replica for each shard, you will have to set up at least 6 Redis server instances so that each shard could get a replica. At this point, we are able to create and operate a Redis cluster. We have learned how to set up automatic sharding and replication for Redis database, thus enabling ability to bear high loads with increased data safety. Also, remember that Redis cluster is a brand new mechanism, so your Redis driver for your specific programming language may not have Redis cluster support. For now, it is possible to play with Redis cluster from Ruby, Python, Java, and PHP languages. Now, we are ready to discuss the last video of the current section, in which we will talk about Sentinel, the way to handle failovers, monitoring, and notification tasks. In the previous video, we have finished discussing scalability, and now we are going to discuss one more important feature of database management systems called failover, which includes failover itself, monitoring, and notifications. While previously we talked about how monitoring can be done with Redis using, for example, monitor command, this command doesn't fit the needs of production systems, especially if you have a lot of Redis servers. One won't be likely to stare at tens of terminals chasing problems in the tails of monitor command output. That is why this process was automated with Sentinel utility, which comes with later versions of Redis DBMS distribution, namely 2.8. Running Sentinel is pretty simple. You only have to run Redis Sentinel executable, which is located along with other Redis executables, and specify configuration file. Sample sentinel.conf file is located at the root of the Redis installation. As we can see from the first messages, the Sentinel tried to monitor localhost on the default port, and after some time has stated that the server is down. As you remember, we have raised up a cluster of 3 servers on ports 7000, 7001, and 7002. So let's edit the configuration file in order to specify one of those servers and then run the Sentinel service again. Now we don't see the +s down message, so the server is up. Let's make an experiment and put the server down and up again. And the monitoring service tells about the server reboot, so the monitoring works. Another way to run Sentinel is to use ---- Sentinel option when starting Redis server, so you can practice with that option on your own. Now let's move to the most interesting feature of the Sentinel, failover. It is configured in the same configuration file. Let's open the file for editing and move to the down after milliseconds option and set master name to my master and milliseconds to 5000. One more thing to tweak is a quorum value, which is the last parameter of a monitor option. It is recommended to use 1 Sentinel per Redis server. In a specific cluster, the server is considered down only if several Sentinels which communicate with each other decide that the server is down. The number is defined by the quorum parameter, and we set it to 1. Now let's run Sentinel again and try to put the Redis server down. So what happens now? When the number of milliseconds specified in down after milliseconds passed, the +s down state is given to the server. Then when failover timeout number of milliseconds passed, the +o down state is given to server and the failover procedure has started. We will pass on the details, but the most interesting is that the error happened, and the error is failover abort no good slave. The problem is that failover works the way it monitors master, then if master is down, it takes one of its slaves and promotes it to master. But we have no slaves here, so the failover procedure aborted. Try to set up a slave on your own or within Redis cluster and repeat the procedure again. The Sentinel configuration is made through a configuration file, but at the same time the configuration can be made during runtime. In order to perform the runtime configuration, we can simply use Redis command line client by specifying Sentinel port, which is 26379 by default. When connected, let's send ping, and the response is pong as expected. The main command supported by the Sentinel is Sentinel command, which has many subcommands inside. First of all, Sentinel can provide information about its state, for example, Sentinel masters, which gives us a list of monitored masters. As we have only one master observed, called myMaster, the result is appropriate. Let's remove our master by typing Sentinel remove myMaster, and then type Sentinel masters in order to see that currently no master is monitored. We can easily bring that master back by typing Sentinel monitor myMaster localhost, which is exactly the same as we have written in the configuration file. You can also operate options with Sentinel set command, specify master name, option name, and value in order to set new value for the option. You can play with values we were setting in the configuration file before. Those are the main abilities of Redis Sentinel service. You can get information about all states and options provided by Sentinel by visiting redis.io/topics/sentinel. At this point, we have learned all basic things in order to scale Redis databases, provide data safety and consistency, and withstand high amounts of queries. This is the last video of the scaling and high availability section, and now we move on to the next section in which we will discuss transactional and pipelined commands execution. Welcome to the 7th section of the Building Databases with Redis video course. In previous sections, we learned about different data types and the operations on those data types provided by Redis. This section is devoted to Redis features such as transactions and pipelining, and we will start with the first one, transactions. In this video, we are going to discuss transactions, which are often critical for application design. First of all, a definition. A transaction is a single unbreakable unit of work performed by a database management system that is not affected by other units of work. In practice, this means that several Redis commands are performed sequentially in an isolated way, such that either all commands are successful or no commands are performed at all. Usually, NoSQL databases don't include transactions in their core functionality and design because they are designed to be extremely fast and scalable compared to classical storage solutions such as relational database. Redis supports transactions that offer all the necessary features of a transaction in a relational database. Atomicity, transaction is treated as a single unit of work. Preservation of data consistency, isolation, other transactions do not affect the current one, and durability. If a transaction is finished, it is guaranteed that all changes are persistent. Let's move on and get to grips with transactions. First of all, let's create two keys with string values to experiment on by typing set key 110 and set key 100. A transaction is a sequence of commands, as we said before. It is started with the multi command, which does not accept arguments. Let's type it in the Redis client. The server replies with OK, which means that the transaction has started. When transaction starts, all commands you perform are not executed immediately, but are queued for further execution as a single atomic sequence that we have called a unit of work before at the beginning of this video. Let's perform two sequential incr commands on key 1 and key 2. This time server replies with a queued string instead of 11 and 101 as it would do if we were out of a transaction. Now, before we finish our transaction, let's open another Redis client and check the values on our keys. As you can see, they are still unchanged, though comments were entered via the first Redis client. That is called isolation, and the isolation itself is ensured between two different clients accessing the Redis database by design. All Redis commands on a certain server are executed sequentially, so the second client won't get data changes before the whole list of commands inside the transaction is executed. So far, we have created our first transaction, and it's time to execute this queued list of commands. The execution of a transaction is performed using an exec command, which does not accept any arguments. Let's type exec to check the value of the keys. This is very easy because Redis replies with the values that were changed during transaction, basically returning the results of commands that were parts of a transaction. And yes, the values have changed. Another way to finish a transaction is not to execute it but cancel it, which is done using the discard command. Let's repeat what was done before in a new transaction. Create a transaction with multi and perform two incur commands on our keys, but this time finish the transaction with a discard command, not an exec. The last reply is OK, which means that the transaction was successfully discarded. Everything is OK when commands do not fail, but sometimes errors do occur. Talking about transactions, there can be two kinds of errors: those that happen before the exec command was executed and those that happen after. The first type of error is handled by Redis, and such an error will lead to the transaction cancellation. The second kind of error, those errors that happen after the exec command call, are not handled by Redis, and the execution continues despite the fact that the command has failed to execute. It can happen if you try to call the rpop command on a key that holds the string value while rpop is only executed on lists. Let's try to make a transaction with this kind of error. As you can see in the example, an error has happened in the first command, but the execution continued, and we received replies for both commands inside the transaction. Let's sum up everything from this video. Transactions are treated as single unit of works with properties such as atomicity, consistency, isolation, and durability. A transaction is either executed as a whole, or it does not affect the database, except in cases where we call commands with incorrect argument. That's all for transactions, and now we are ready to continue with the related topic, which discusses a typical check and set problem and how it is solved using Redis. In the previous video, we talked about transactions, and the main property of transactions we mentioned was their ability to perform a continuous series of commands, and no other client can break the sequence until it is executed. So this property of transactions is extremely useful when you have to be sure that no key involved in a transaction is changed by another concurrent client. This is the place where the famous check and set problem appears. Let's define the nature of the problem. Assume you have a number stored in a key inside the Redis database. You have to multiply this number by 3 if the number is even, and by 2 if it is odd. First of all, in order to solve the problem, we have to read the number with the get command, then we perform some application logic, and finally use set to update the value. The problem is that there is a time gap between these operations, so between get and set, another client can perform operations on current value, and you cannot be sure that your data will be consistent afterwards. This is a widely known concurrency problem called race condition, which basically means that the result of a calculation depends on the working of the other two executors. In our case, we talk about the Redis client running commands on the Redis server. In this case, even transactions do not help, because the application's logic is performed between these operations and they cannot be just done strictly sequentially. This example with even and odd numbers is not quite universal, but demonstrates the problem that we cannot solve using the knowledge we attained in the previous videos. Still, some part of these solutions can be done using standard Redis commands. Almost every command that sets some value has its version within an x suffix. For example, setInX command sets a value only if the key does not exist. It is also a check and set problem, but it has a better solution using one standard command. Let's look at the example on screen in order to see how the command works. Other commands with a similar functionality are hsetInX, msetInX, and renameInX. So this is the point where we can use watch command. This command allows us to specify keys that will later be affected by a transaction. The watch command accepts any number of keys that you plan to work during a transaction. The main purpose of a command is to fix things if watched keys were affected by commands outside of a transaction. Let's add two keys with sample integer values to the database by typing setKey110 and setKey200. Then let's specify both keys to be members of a future transaction using the watch command by typing watch key1 key2. You can also perform the same with two watch commands separately for each key, but using a single command is obviously more efficient. Before we start making transactions, let's mention that those keys can be unwatched using the unwatch command. It does not take any parameters as it unwatches. Performing unwatch clears all of the watched keys for the current client. Let's perform the command and then watch the keys again for further work. The watch command does not work without transactions, so it only affects keys that are involved in commands contained inside a transaction. So let's start a transaction with the multi command. Now we are ready to perform some operations. Let those be incr key1 and incr key2. The server replies with queued both times. In order to finish our experiment, we open a new Redis client instance and perform a command on, for example, key1. Let it be set key1 1. Now we go back to our original client in which the transaction is created and perform exec in order to commit the transaction. The answer is unexpectedly nil, which means the transaction has failed. Also note that the command from the second client has succeeded, but both commands from the transaction have failed due to the atomic nature of the transaction. This is how watch works, basically not allowing transactional operations on watched keys. The example speaks for itself, but we have still not shown a check and set problem solution. Well, consider it to be a small homework task. Use the programming language you prefer in order to perform a simple script that will solve the check and set problem. Now we are going to continue this section with the next video in which we are going to discuss command pipelining. In the previous video we were talking about the popular check and set problem, which is solved using the watch command and transactions that are implemented in Redis with multi and exec commands. This video, along with the next one, brings us to the second part of the current section, which starts here with the commands pipelining technology that Redis offers in order to optimize command execution speed in certain situations. Let's start with the basics of how a Redis command is executed. Redis is built on a request-response protocol, which basically means that every sent command must be followed by a response from the server. The only exception is a situation with transactional execution when commands are queued and then executed, but still the reply keeps responses for every queued command, not for a transaction as a whole in case the transaction succeeded. And actually the problem is hidden here, because every command makes a round trip from client to server and back, taking time to send data back and forth, taking more input-output operations, which decreases the ability of such systems to carry high loads. Pipelining is a technology offered by Redis server that fixes this problem by sending several commands at once, and it is important not to mistake pipelining for transactions, which just queues the commands up and then executes them. Pipelining is basically a way to send next commands before waiting for a reply from Redis on the status of the previous commands. There are basically two ways to achieve the effect of pipelining: using the netcat utility from the terminal, or some other utility that supports sending plain text over the network, or writing a script using any programming language that has drivers supporting the Redis database. Let's try with the first one. So the first way to achieve pipelining is to use a standard netcat utility that is represented by the nc standard command in either Mac OS X or Linux operating systems. If you're using Windows, you will have to install the Cygwin toolset, which brings the Unix subsystem to Windows OS. Using netcat, we open TCP connection to Redis server and are able to send raw Redis commands into the opened connection. In order to pass a list of Redis commands, we use printf utility and pipe, which pushes the printf command output into netcat input. The result you can see on the screen. We have passed 3 commands to increase value stored in the pp key by 1. The server replied with 3 answers. Let's run Redis client and get the pp key value. Here it is. The value equals to 3. The advantage we have received from such a style of command execution is that we had only 1 request and 1 response. Instead of 6, we could have sent in 3 commands separately, making for greater efficiency in the input-output commands and slightly increasing performance. Now let's inspect another way to do the same, a pipelined command execution. The example is a Python script in a pipe folder. The script has one function that creates the pipeline object, adds 10,000 commands to that object, and then executes those commands in pipelined mode. The main block of the script executes that function and prints the value of some key. The script pretty much does the same thing we did using only standard command line utilities, but looks more programmer-friendly. Let's run the script. And here we see that the commands were executed successfully. So far, we have managed to improve performance of a command series by using pipelining, either running it using netcat or via a Python script. While it can look weird why we did the job using command line utilities first, but it serves 2 purposes. First, we now have a better understanding of the Redis internals and what is the nature of pipelining in terms of the Redis network protocol. And the second, it can be really useful in production, which we will see it in the next video. In the previous video, we talked about features supported by the Redis database, such as pipelining. We have also managed to figure out that Redis pipelining serves as a means of command execution that increases performance. It is not a coincidence that this section in which we discuss mass insertion of data comes right after the video on pipelining. That is because the mass insertion of data problem is solved via pipelining in the Redis database. So let's talk some about the nature of the problem. It often happens that when a new project is deployed to the production environment, its storage cannot remain empty. For example, imagine we are developing a proxy server that supports blacklist IP filtering. This means that we have to match the incoming connections by all IPs in this table and see if they are already on the blacklist. If so, we just deny the client connection to our server. Usually, such tasks can start this way. We already have dozens or even thousands of IPs we already know about to be blacklisted. We have to add all of these IPs into the database, but we obviously cannot do it manually entering each IP address one by one, as that would take months to do. Redis allows us to perform the job by offering pipelining, and it implements it also via the Redis command line client, which was not covered in the previous section. In order to start Redis in pipeline mode, we have to pass the --pipe option to the Redis CLI command. As you can see now, Redis does not offer you to enter commands, it just waits for the data input in order to consume it and execute commands in a pipelined manner. Now let's move directly to the task. We have an ips.txt file in the mass folder of the examples, which we have to insert into Redis, where IP addresses are keys and values are strings with integer 1. Now we have to write a script which generates raw Redis protocol commands and prints them into standard output. Actually, the script is located nearby in the mass.py Python script. First, we define a pattern. It is a pattern of the Redis set command. Let's discuss it. *3 is a number of strings sent to the server. In our case, those are set, key name, and key value, which always equals 1. Next, we have 3 blocks denoted by $signs. A number after $sign is a string length in bytes. After each $block, we add an actual value. Those numbers in curly braces represent the Python syntax for a string pattern used by the format method further in the code. We pass the IP string value length in bytes and then the string itself in order to generate a command. Also, each block and each separate command must be terminated with \r\n or the carriage return and line feed characters. Let's run the scripts and see what they produce. Here what the command looks like. First, number of blocks, and then the length and values for those string blocks. Very simple, I think. For the last task, let's make the script work for a mass insertion problem solution. All we have to do is to pipe it into the Redis client, and the server replies with the status 0 errors and 4 replies, which means that we have successfully completed the job. Mass insertion of data using the Redis client pipe mode is a very powerful tool, as it is the fastest way to insert data into the Redis database. At this point, we have finished talking about mass insertion of data, and we have also finished our whole section in which we have discussed topics needed to design and develop high-loaded distributed real-life systems. And now we are ready to move to the last section of our video course, in which we will discuss how to use the power of the Lua programming language in order to extend Redis standard functionality. Welcome to the 8th section of building databases with Redis, called Scripting Redis. And this is the last section of this video course, in which we are going to discuss how to extend Redis with additional functionality. We are going to devote the first 2 videos of the section to introduction to the main features of the Lua programming language, which will allow you to write your own scripts in order to solve quite complex problems that are not optimal if solved by a sequence of Redis commands. In the previous sections, we were talking about transactions and pipelined command execution as a way to optimize communication between Redis clients and servers in order to get more efficient problem-solving systems. Another method for optimization is to use server-side scripts written in the Lua programming language, which are able to execute more complex business logic that can be done by a sequence of built-in Redis commands. The Lua programming language allows us to write extensions which the Redis server is able to execute. Such extensions are implemented as scripts written in the Lua programming language, which Redis can execute on the server, giving you access to the data stored in its database. First of all, we have to get the Lua interpreter binary from the lua.org website. On the website, click the download link and find the binary section on the download page, where you can find Lua interpreter binaries. If you're on Linux, you might already have the interpreter installed, and you can check whether it's there with the which Lua command on the command line. If the command prints nothing, then you don't have an interpreter installed. However, if it's installed, the command will print you a path to interpreter and it's ready to be used. Now, as the Lua interpreter is ready to use, let's create our first script and run it. To do that, we can use our favorite text editor. Here in videos, we will continue to use Sublime Text 3. Let's start with the traditional Hello World script as it is shown on screen. Here we use a built-in print function that is called, and one string parameter is passed to it. In order to run the script, we go to the command line, invoke the Lua interpreter binary, and pass a path to our script. As we now can see, our script works just fine, printing the string as expected. Let's continue and make a decent but at the same time concise overview of language features that will allow us to create Lua scripts from the very beginning. First of all, Lua stores data in variables, and you can declare and initialize a new variable by specifying its name and using an assignment operator. As you can see here, we can use the print function not only for strings but also for other types, in this case the numbers and nil type. Such variables declared on the highest level of a module are called global variables of the script. Lua supports the next data types: nil, which basically means no value; boolean, that can hold results of logical operations, which are either true, false, or nil, as equivalent to false; numbers; strings to store textual data; tables, and functions. Also, Lua is a dynamically typed language, so you can reassign a new value to an old variable even if they have different types. As you might have noticed, the most complex data type here is a table. A table in Lua is almost absolutely equivalent to hash type in Redis, when you have a unique set of keys mapped to a set of values. Rows from 10 to 12 in the source code show us how to initialize and fill a table, while row 17 shows how can we retrieve a value from tables by keys, either using square brackets or using the dot operator, if a key is a valid identifier that can be used to name Lua variables. Now, let's talk a bit about operation on other data types. First, let's discuss booleans. Booleans are result of comparison, lines 5 and 6, and logical, lines 7 to 8 operations. They're also used to make decisions in conditional code execution, which we'll talk about in the next video. The next data type is numbers. Numbers are floating point numbers that act like numbers in mathematics. You can use them to do calculations, like shown on the screen. You can also use round braces in order to change the precedence of operations. By default, they are the same as in mathematics. Multiplication and division go first, then addition and subtraction. Now let's move to the strings. Strings represent textual data, like assigned in first two lines. Lua allows the concatenation operation, gluing two strings, with the dot operator. We can use double square brackets instead of double quotes in order to say that it is a string without escaped characters. Also, such strings can be written in a multi-line manner with line breaks added into string as shown in terminal output on the screen, while escape characters are shown as is without interpreting. Apart from concatenation, there is a built-in string library that contains functions that operate on strings, and the most popular are find, which returns position of the second string argument in the first one, or nil if the second argument is not a substring of the first one, and format that performs placeholder substitution as shown in line 13. That's all on basic data types that the Lua programming language supports. Now you will be able to perform calculations and simple text processing using the Lua programming language. Now, we're moving to the next video in which we will discuss Lua instructions flow control statement. In the previous video, we started discussing the Lua programming language and we learned how to install the Lua interpreter, run Lua scripts, and how to operate data represented by basic data types. We also discussed the assignment statement. In this video, we are going to cover more complex statements in order to achieve branching and loop code execution, which will allow us to write more complex data processing algorithms. Branched and loop code execution is a basis for almost all imperative programming languages. In Lua, code branching is achieved by using if-else statements and if-else expressions. Let's start with the if statement. The if statement has a simple syntax, starting with the if statement, which is followed by a conditional expression that must evaluate in some Boolean value. If that value is true, the very next block is executed. If not, other branches of if statement are checked and executed. Else if is used if there is more than one condition to be checked, with the last one being the else block, which is executed when none of the previous conditions were met. Let's run the script and see the result. As you can see, although either the first or second conditions satisfy our if-else statement, only the first block is executed. That is how the if-else statement works. Only the first block for which the condition is met is executed, others are not. It is also important to mention that else if and else blocks are not mandatory, so only if and can be present when using this statement, like shown in lines 12 to 14. When a condition has only if or if and else blocks, the if statement can be simplified and used as an if expression, which can be easily written down in one line. If expressions are possible because of the reduced evaluation of logical expressions. Let's look at those three lines, 17, 18, and 21. In the first one, print is executed if x more than 5 is met. In the second one, only the second expression is executed and has a higher precedence than or. So the result of AND operation is false and the first print is not executed. And in the last case, both prints are executed because either AND and OR return true. That's all on branched code execution, and now we are ready to move on to the looping statement. First of all, let's talk about looping. Loops are an essential feature for a programming language because they allow execution on a block of code for different iteration variables. For example, let's assume we have a table of numeric values and we have to find the sum of those values. The problem is that we do not always have a fixed number of steps here to receive a sum of those values. That's why we have to perform addition several times, and it is called looping. The first way to perform a looped execution of code is to use the while do statement. The code block is executed while the condition is met. Here we have the hash character, which returns the length of the table when the table is treated as an array. It takes succeeding keys from 1 and until the value for the key appears to be equal to nil. In our case, the length is 3. The counter variable is used to count steps. Apparently, we have to do additions while the counter is less than or equal to the table length. The sum variable stores the needed result for our algorithm, which we are printing at the end of the script. The next way to do the task is the repeat until statement, which is similar to the while do, but the condition is put after the body, so the code block is executed at least once. Also, the loop continues to work until the condition is met, which is the opposite to how the condition works in the while do algorithm. And the last kind of loop is a for loop, which has two variants, a numeric for loop and an iterator for loop. A numeric for loop is used when we have to iterate over a set of numbers from a minimum to maximum value in some step. Here, how we can solve our task using the for loop. In our case, the step is 1, the third number of the for loop. So we could have just omit this value, because 1 is the default value for the iteration step. And the last way to create a loop is in iterator loop. It cannot directly use tables, so we use the iPairs built-in function in order to receive an iterator from table 1. iPairs produces pairs of keys and corresponding values, so it allows us to iterate over keys and values simultaneously, which is shown in the script. Here we do not declare counter variable, but use it inside the iterating for loop. Such a loop iterates over all values, so we do not use counter to create any kind of conditions. That's all for loops, and now let's discuss the last feature for this video, functions. Functions are independent code blocks that are executed on different arguments. We have actually been using functions so far. For example, print is a function, and we have seen that it can be used with different arguments to print anything we want on screen. Let's change our code to be reusable by designing a function. As you can see, we have created a new function, summator, which takes one argument and returns a calculated sum. The function was called 2 times for 2 different tables, which allows us not to repeat the whole loop block of code as many times as we have to calculate a sum of value. Here is an overview and discussion of all the core features the Lua programming language offers that are good enough to start writing even complex scripts for the Redis database server, and that is one topic for our next video. In the previous videos of this section, we discussed the core features of the Lua programming language, and we have stated that we need this knowledge in order to be able to extend the standard set of Redis database server commands with new ones for our specific needs. First of all, we need to specify where can we get input for the scripts and where we put output of the script if we want to process data. When we are scripting in Redis, we receive our input from 2 sources, the Redis database and script arguments, and we can perform an output operation as a Redis database reply. It is important to understand that the Redis and Lua data types are still different, so there are rules of conversion that you have to follow. Those rules are a bit different depending on the way of conversion, from Lua to Redis or from Redis to Lua, as shown on the screen. Now that we know how Lua deals with Redis data, let's move on and get into evaluating scripts. The first way to evaluate a script is to do it from the command line client. Let's write a simple script that returns a static string. The answer is in a similar format to what we could have received using Redis get command. This is an eval command that takes variable number of arguments. The first argument is always a script itself. The second is a number of Redis keys that we are going to pass to the script to operate on. In our case, it is 0. Let's make it a more complex script and pass a key to the script. Here we can see that our script takes one key argument and it is accessed via the keys table, whose keys are succeeding integer numbers starting from 1. And the reply is an argument name. but we have also set a value for the key called name earlier, and it would be cool to take that name from DB. Redis allows it with Redis.call and Redis.pcall functions, which differ by how they process exceptional situations. We will use Redis.call here. This function takes any amount of arguments corresponding to Redis commands. Let's look at it in an example. We have changed keys1 to Redis.call get keys1, which is the same as if we called getName from the command line. You might be wondering why we have to pass a number of keys we are going to work with to the Redis script, but it is a trade-off between the ability to run script on a Redis cluster without errors and scripting subsystem usability. Also, apart from passing keys, you can pass other arguments that follow a list of keys to the Lua script. Let's change our hello script to be even more customizable. Here we don't hardcode a greeting, but pass it via an additional argument, still passing a number of keys as one to the script. You can use any number of additional arguments in scripting. Also, we have to mention that Redis scripts are executed atomically, basically using the same interpreter to execute each command, so we can think of a set of commands executed during script execution as a transactional way of execution commands. And the last important thing is that Redis scripts must act like pure functions, so they must give the same result if the same set of arguments is passed into the function. This basically means that you're not allowed to use functions that takes up the system's time or that generates random numbers. Here, we have discussed and executed several scripts on the Redis database server using the Lua programming language. While the examples in this video were very simple, they demonstrate basically everything you need to know about how to access Redis data storage from Lua scripts. We are ready to move to the next video of this section, in which we will discuss how to cache reusable scripts on the Redis server. In the previous video, we discussed how to build a bridge between the Redis database and the Lua script. We have managed to write some reusable scripts that can take different arguments and get access to Redis data storage via calling Redis server commands. Using the eval command is quite handy when we have a script to perform rarely or when we need to perform a one-time script. But imagine that your script is more complex and quite large, and you have to execute it as often as any other Redis command, such as get. Then it is quite expensive to send the script over the network every time. That is why Redis offers a script command that allows us to upload scripts to the server and cache their body there. After that, you're able to call a script not by sending the whole script body, but only a short string calculated from the script body with a hash function. Let's start using the script command by loading our simple script onto the server. It is done by the script load command, which accepts a script. Let's load a script from previous video, as shown on screen. Note that we do not provide arguments here. As a reply, we have received the SHA hash of the script, which had the same length for all scripts and is not dependent on the length of the script's body itself. Now we can make check whether the script exists on server using the script exists command. Let's try it using the received hash. The server replies with 1, which means the script exists. The same is not true for any other hash value. We try some other string and we receive a reply of 0. In order to remove scripts from server-side cache, we have to use the script flush command. The only disadvantage of the command is that it removes all the scripts from cache and is not able to remove a single script. Now let's proceed to the execution of cached script. This is done using the eval sha function, which receives a hash code of the script and script's arguments. Let's execute our script using the eval_sha function. The call is similar to that of eval, but instead of the script's body we passed script's received hash as a reply from the script load function. As you can see, the script executes in the same way as using eval. Talking about scripts, we must always take into account that standard Redis commands are absolutely predictable and do not produce any errors. On the other hand, custom Lua scripts can have errors, and their processing time depends on the quality of the algorithm of the script. That is why, when writing scripting, we have to be sure that it does execute for a predictably small amount of time. But if there is still a situation where an infinite loop happens inside a script, or a script executes for more time than expected, Redis offers the script kill command, which receives hash as an argument. Also, scripts can be a good way of optimization. If you have to pass a lot of data from the server to the client, and it would be wiser to process that data on the server, you must consider writing a script for that use case. So, seeking a trade-off between using network bandwidth and server CPU time is the biggest challenge when deciding whether to write a script or to use a set of standard commands either in plain or transactional mode. That's all on scripting Redis, and at the moment we have finished all topics of this video course. Welcome to the last video of building databases with Redis. So far, in this video course, we have managed to discuss all the essential features of working with Redis databases from the perspectives of either a software engineer or a system administrator. During the course, we have discussed data types supported by the Redis database management system, almost all Redis commands, and others are just variations of those we have already covered. We have also looked at the real applications that use Redis as a main source of storage for them, a simple wiki application and an image gallery application. Building Redis clusters either manually or using the Redis cluster system should also be familiar to you. The final topic that we have covered was Redis Lua scripting, which is a fantastic way to extend standard Redis behavior and enrich it with your application-specific routines. Now, you would be able either to build Redis storage for an application or support and configure either a single Redis server instance or a whole cluster in a reliable and resilient manner, depending on what your role on the project is. My advice is not to stop here and try to begin implementing Redis in a real-life project. The more problems you discover, the more things you learn. Also, remember to visit the Redis.io website, on which informative tutorials, manuals, and specifications for all Redis subsystems can be found. I consider Redis.io to be a resource that helps you to solve 99% of your problems. Thanks for watching the whole video course, and good luck using Redis in real software projects.